In this lecture, we will discuss about the memory system performance using the cache memory. Okay. So before that, we should know that what is heat rate, cache access time, miss rate, and miss penalty. So when processor generates one request, first it searches in the cache. So what is the bit rate of that? Let's say H. And if it is getting in the cache, then what is the access time of the cache? TC. If it is not in the cache, what is the chances of that? 1 minus S, that is called miss rate. If it is, then you have to access from the main memory, that is main memory access time, or you can say it is also called as the miss penalty. Okay. So what is the average memory access time formula? So TC plus 1 minus H into TN. So that means cache hit time plus miss rate into miss penalty. So already you know this formula from the computer organizational architecture topic. Okay. Now how to calculate CPU time with the involvement of cache. So CPU time is equal to what? Total number of clock cycles into clock cycle time. So how to calculate total number of clock cycle? So how much the clock cycle in the CPU and how much the memory stall cycle. Just addition of that CPU clock cycle plus memory stall cycles. Now for the CPU clock cycles, so we are calculating from the ideal CPI, that means clock cycle per instruction, and number of instruction, that is IC into ideal CPI. So this is your CPU clock cycles. Now how to calculate this memory stall cycles? So for the memory stall cycles, how will calculate? So in the program, how much misses, number of misses in the program into miss penalty. Okay. If there is miss, then how much time will take to get extra data from the main memory? That's the miss penalty. So number of miss into miss penalty. So now, so if we talk about the for instruction, number of miss, it is for the for program. So for instruction, so number of miss for instruction. So that's why you multiply instruction count. So IC into number of miss for instruction into miss penalty. Okay. Now, so what is this number of miss? Number of miss in terms of miss rate. So see. So miss rate is what? Number of miss per memory access. Okay. So let's say from the 100 memory access, how much miss you get. Okay. So that means number of miss per memory access. So that is your miss rate. So if you find out number of miss is equal to miss rate into memory access. Okay. So first please remember. So miss rate is your number of miss per memory access. So that's why number of miss is equal to miss rate into memory access. So just put this number of miss here. In the place of number of miss, what you put? Miss rate into memory access. And for instruction into miss penalty. Now see. So when I open the bracket, so how it look like? Memory access for instruction into miss rate into miss penalty. Okay. Into IC. So this is your memory stall cycles. If I say memory stall cycles for instruction, that is means memory stall CPI. So just to remove this IC, that means memory access for instruction. So in one instruction, how many memory access? Into miss rate into miss penalty. Okay. Now, in the term of CPU time or CPU time, so CPU time is what? IC into ideal CPU for the CPU clock cycle. For the memory stall cycles, it will be this formula. IC into memory access for instruction into miss rate into miss penalty. Okay. If we are talking about the CPU time for instruction, okay, for one instruction, how much CPU time? Just remove this IC, that means ideal CPI plus memory access for instruction into miss rate into miss penalty. Okay. So this is what the formula of CPU time and CPU time for instruction. So main formula is this, how to calculate this memory stall cycles for instruction. Okay. So anyhow you have to remember memory access for instruction into miss rate into miss penalty. Okay. And how we are finding this? So we have explained from this part. So you should know this one. Okay. So if the question will come according to the number of miss for instruction, so you just use this formula. Number of miss for instruction into miss penalty. Okay. If it is given in the term of miss rate, miss penalty, so you use this formula. Okay. So either you have to remember this one, also you have to remember this one. Okay. So according to the question, you will solve it. Now, we will solve some numerical problems based on this formula. In the first example, see, so ideal CPI 1.0. So when all memory access are hit in the cache and data accessed by the load and store instruction, that is the percentage of program, that is 50%. That means 50% of the instructions are load and store. Then miss penalty. Now I will show you one example based on the formula. So ideal CPI is 1.0 and load and store in the program is 50%. That means 50% of the instructions are load and store. Miss penalty is 25 clock cycle. Miss rate is 2%. And compute how much faster it will computer be if all the memory access are hit. Okay. So this is the actual computer where we are getting the miss rate and miss penalty, and here we are getting all the cache hit. So first find out our actual computer, original computer. So what is the CPI? So ideal CPI. So there is a formula I have written in upper. Ideal CPI plus memory access per instruction into miss rate into miss penalty. Okay. Now, so what is ideal CPI? Ideal CPI is given 1.0. Now, so what is memory access per instruction? This is the important part. So what is memory access per instruction? So for one instruction, how much memory access you are doing? Okay. So first of all, we are getting from PC to IR. So from PC to IR, one memory access. For what? To fetch, actually instruction itself present in the memory. So to fetch the instruction, so we need one memory access. Okay. To fetch the instruction, we need one memory access. Okay. Now after getting the IR, what is the chances of load and store? Okay. What is the chances of load and store? So here in the example, it is in the 50% load and store. That means, so this is for this instruction again we will access the memory. Got it? So first of all, to fetch the instruction 1 and for the load and store it is 0.5. Now, so as here miss rate is giving only 1, that means it is for the instruction miss rate is same as for the data miss rate. Okay. So instruction miss rate is 2% and data miss rate is 2%. So we can do, so without partition this formula, we can do what? 1 plus 0.5. 1 plus 0.5. So 1 for what? I am still writing here. 1 is for the instruction fetch. This 0.5 is for the 50% load and store. And miss rate is given 2%, that means 0.02. Miss penalty is given 25 clock cycle. So understand. So we might confuse regarding this one. 1 is for the instruction fetch, 0.5 for the load and store. Means actually we are extracting from the PC to instruction. So PC contains the memory address. So what is the instruction present in the memory address? That is called instruction fetch. So for that we are getting one memory access. So for one instruction you will get one memory access for the instruction fetch. Now after fetch, that means instruction present in the IR register. Now what is the chances of that? There is a load and store instruction, because there is other instruction like ALU, control, but for that we will not access the memory. Only load and store instruction are accessing the memory. So what is the chances of that? 50%. That means 0.5. Okay. So why we are adding them? Because as we have only one miss rate. If you have different miss rate, then you have to partition the formula. Okay. So we see the next example. Got it? Now, so just evaluate this 1 plus 1.5 into 0.02 into 25. So answer will be 1.5. 1.75 clock cycle. 1.75 clock cycle. Now, how much faster? So, for the performance, so this is your CPI for the original computer divided by our ideal CPI, that is 1. Okay. So, this is 1.75 for the what? CPI for actual computer. This one for what? This is your ideal CPI basically, where all cassette. So you can say that your computer which has no miss rate, that means all are cassette, is 1.75 times faster than the original computer. So what you can say that the computer which computer where all cassette is 1.75 times faster than the computer where the miss rate is involved, and the computer where miss rate are involved. Okay, just see, we are getting the 1.75, then how much faster? 1.75 divided by the ideal CPI, it is your 1. So this is your 1.75 times faster than the computer which is involved with the miss rate. Now, just see, now we'll go for the second example. So second example is, just read, clock rate is 200 megahertz. Clock rate is 200 megahertz. Ideal CPI is 1.1 and 50% arithmetic and logic instruction, 30% load and store, 20% control, and 10% data memory operation get 50 clock cycle penalty, and 1% instruction memory get the 50 clock cycle penalty, compute CPI and AMT. So what is the CPI? So what is this 10% and 1%? So this is your miss rate. Miss rate of what? Data. Miss rate of data. So this 1% is the miss rate of instruction. Okay. Now, just calculate the CPI. So I am not writing the formula again. So CPI is equal to ideal CPI. Ideal CPI is 1.1 plus, as we have two miss rate for the instruction and the data. Okay, we have two miss rate. But in the previous example, here is only one miss rate. So that's why I added here. Now, here for the instruction we write. So memory access per instruction is 1 into miss rate of the memory access for the instruction 1%, that is 0.01 into miss penalty is 50. Now, memory access per instruction for data is 30%. So 0.3 into miss rate for the data is 10%, that is 0.1 into miss penalty is 50. Just see, here 1 and here 0.3. Why I am partitioning? Because we have different miss rate. Here miss rate is 1%. This part is for what? Instruction. This part is for the data. Okay. So 1% instruction miss rate, 10% miss rate for the data. Okay. So just calculate this thing. So you get the answer is 3.1 clock cycle. 3.1 clock cycle. Okay, so this is the CPI. Now, how to calculate average memory access time? So, to calculate the average memory access time, the formula is percentage of instruction, cache time plus miss rate into miss penalty plus percentage of data, cache time plus miss rate into miss penalty. So, what is this percentage of instruction, percentage of data? So, I am writing here what is the percentage of instruction and percentage of data. That means, if you say that from the 100%, from the out of 100 memory access, how much memory access for the instruction, how much memory access for the data because of the data. How much memory access for the instruction, how much memory access for the data. So, as you know, our total memory access per instruction, is 1.3. Yes or no? Total memory access per instruction. Your total memory access per instruction is what? 1.3. So, from where getting 1.3? So, 30%, that means 1 plus 0.3. 1 plus 0.3. So, we are getting 1.3 memory access per instruction. Now, we will say what is the, from that, what is the percentage of instruction? That means 1 upon 1.3. You are assessing total memory access per instruction 1.3. And what is the percentage of instruction? Because of that, 1. Same for the data, 0.3 by 1.3. Just see how we are finding. 1 upon 1.3, 0.3 upon 1.3. So, what is that? 1.3 is your memory access per instruction. Okay. So, if you say that our memory access per instruction is total, then from that, what is the percentage of memory access because of the instruction? Because of the instruction, we are accessing the memory. What is the percentage there? Getting it? So, to calculate this thing, so your total memory access, and the numerator will be 1. Because it is always will be 1. And for the data, 1.3 and numerator will be how much load and store. How much load and store. Just put the values 1 upon 1.3. Cache time. So here cache time is always equal to ideal CPI. So ideal CPI is 1.1. We can just write down here. If it is not given explicitly cache time, you just take the assumption then it will be ideal CPI. Okay. So 1.1 plus miss rate for the instruction is 0.01. Miss penalty is 50 plus 0.3 upon 1.3, 1.1 plus 10%, 0.1 into 50. So, this is your average memory access time. So, what is the answer for the average memory access time? 2.63. 2.63 clock cycle. Okay, this is what we are calculating average memory access time and CPI. Just see what is the difference between two examples. Here, one miss rate is given. That means this is for the instruction miss rate and this is for the data miss rate. So, we can combine these two. 1 plus 0.3. So, here 1 plus 0.5. Because here the miss rate are the, in that example, miss rate are same. Now, so how are you calculating? Just put the values in the formula. Now, for this case, one is as the miss rate is different, we have to partition for the instruction and data. This is the CPI. Now, for the average memory access time calculation, just remember the formula is percentage of instruction and your average memory access time formula, then percentage factor, then average memory access time formula. So how to calculate this percentage of instruction? Here. It is numerator is always 1. Remember, numerator is always 1, and whatever the denominator, denominator depends upon how 1 plus the number of load and store instruction. Okay, 30%, that means 0.3. Okay, so this is what we are finding. Just put the values and you will get the answer. Now the third example based on the same concept. Okay, so the given is 20% load and store instruction. CPI without memory store is 1 cycle. That means it is ideal CPI. Cache miss penalty is 100 clock cycle. Miss rate is 1%. Memory, then calculate these three things. Memory store cycles for instruction. CPI with cache. CPI without cache. So first calculate memory store cycles for instruction. So what is the formula for the memory store cycles? That means we are talking about this part. Okay. Memory access for instruction into miss rate into miss penalty. So just put the values. Memory access for instruction is what? So as we are using 1 miss rate, so just combine this. So 1 plus 20% load and store. Okay. Then miss rate is 0.01. Miss penalty is 100. That means 1.2 clock cycle. This is your what? Memory stall cycles for instruction. Now CPI with cache. CPI with cache is what? Ideal CPI plus memory stall cycles for instruction. So ideal CPI is this one. That is 1 plus 1.2. That is 2.2 clock cycle. Got it? Now, how to calculate CPI without cache? That means in the system only processor and main memory. There is no cache. So that means for each memory access, you have to access what? Main memory. You cannot access the cache as there is. We are talking about there is no cache. So first ideal CPI plus then how much memory access you are doing. How much memory access you are doing? Where memory access we are doing 1 plus 0.2. That means 1.2. Yes or no? For instruction we are talking about now. For one instruction we are accessing 1.2 memory access. For each memory access you have to access what? Main memory. Getting it? So what is the main memory access type? That means it is talking about the miss penalty. Okay, that is 100. Okay, so what is the answer? 1 plus 1.2 into 100. That is 121. So 121 clock cycle for the CPI without cache. Okay, let's see. So this is your based on the concept.